Okay, all right, you're all set.
All right, cool. Hello, so my project is Pill Pusher. It is pill classification using SimCLR contrastive loss with textured pre-training. So I'll briefly go over the motivation. So the NIH hosted a pill image recognition challenge in 2016. After that, there was another benchmark created called ePillID, which is the one that I'm targeting. This used curated data from that challenge and another data set owned by them. And it is a few shot data set, a lot like the original, which means that you're given a limited amount of data in order to make your predictions. And so for here, all you need to know from this is the number of consumer images that you're given is extremely limited. And also the number of images in the data set as a whole is a lot less than like ImageNet or any of those other benchmarks normally used. And so this is a ranking type problem. You can do it as classification, but that makes it harder. A bit trickier anyways with the limited data. So classification, as a recap, is just where you take the images that you're given and you label them according to some predefined labels. Ranking is a bit different in that we're trying to gauge a similarity between these images and what are called reference images, represented in the previous figure here by this upper part, these reference images. And so once you do pair it with one of these reference images, what you're essentially doing is like ranking the similarity between these three or however many different reference images there are. They'll each have a label, and then you can think of it as classification past that initial step. And like I mentioned before, a lot of this initial data is missing during training. So the way you approach the problem is very important. So one idea I had at the beginning of the semester was I wanted to try some kind of contrastive learning with a synthetic background. And so the idea here is I want to take a large number of previously segmented pills, do a little bit of regular augmentation, and then slap them over different backgrounds. And the rationale for this is I want to aggressively teach the network what is and what isn't a pattern of a pill. So for example, if I have these two images here, we can see that there is a pill here and a pill here. I want to also let the network know that these figures in the background are not important. And the way that this is going to happen is the network is going to repeatedly see images that look like this pill, but every time this pill shows up, it'll have a different background. The other idea I wanted to explore was new data availability. And a lot of the literature I was reading for this project, it seemed like at the time, like 2016, maybe to 2020, there wasn't a lot of data available. And I'd wondered if that changed. There is this data set, which I found, which is the C3PI data set, which has 41,000 images, although only about 4,000 unique types. So it does have a lot of images, but there's not a ton of variation. But it comes in this really nice format where I can really easily crop out this pill from the center and then use it to create a synthetic data set. And the ePillID benchmark does come with a segmentation set of its own that is arguably better, but it was extremely hard to utilize because of kind of weird artifacts. Like, I don't know what happened to this image over here. And then these, it was really difficult to pull out the background because the background will bleed into the labels on the images. And I'll mention this is the data set I'm using for textures. It's just another data set on the internet called the Describable Textures data set. And so the training goal here is SimCLR. In my entire process, this is essentially what I use. So we take some image, perform two different augmentations on it, and then we want to maximize the agreement between those two images while also pushing away all of the other images in the same batch. And then this will break out into a two-step process for me. First, I'll do a large self-supervised pre-training on C3PI, and this is the synthetic data set that I'm generating with the fancy textured backgrounds. Then it will be, I'll do a fine-tuned or supervised training on ePillID. This will still be using SimCLR or something very close to it, but this will be using the actual data for the benchmark. And then of course, there's an evaluation step. And as far as my experimentation goes with this project, it's just going to be how important are each of these blocks. And so depending on how much time I have, I'll try not doing the self-supervised pre-training here, or maybe not doing this training and seeing how that impacts the evaluation. So the self-supervised pre-training on the large synthetic data set is like this. You pick a random pill and texture, resize both appropriately, do a random perspective shift on the pill, which you can think of as taking the pill as a 2D image and then moving it to 3D and kind of wiggling it around a little bit. Then we overlay this pill onto the texture at a random location. I don't do any augmentations to the texture because I didn't think I needed to. And then we go back to SimCLR, you rank the similarity of the images and use that as the loss. And so here is an example of a batch, but I actually, about 30 minutes ago, grabbed a batch from Newton because it is currently training. And so the batch size is 256 because SimCLR does need a massive batch size, but it's actually really neat how well it's been able to distinguish these augmentations. Like this is one that I always end up looking at with this R. Like even though the color has shifted quite a bit, it still looks like it recognized this symbol in the center. And most of these, it actually looks like it got right, even like really color shifted ones like this one, which is pretty cool. And here you can see the perspective shift. It warps the image around. And these are intended to mimic the consumer images because these are all reference images. And that's intended to play out on the evaluation. Then the supervised training, the fine tuning part where I actually use the benchmark data is similar. I either pick a consumer pill, match it with a reference pill, augment each, or maybe, I don't know if I'll actually augment them or not. I have not implemented this part yet, but then do the SimCLR again and just try and get the link between consumer and reference to be made. And because there's not a lot of consumer pills, I also have to do training with the reference pills. So this will all be in the same epic, same training cycle, whatnot. Pick a reference pill, augment it twice, and then again, do the same SimCLR. Everything here is as close to the SimCLR method as I can get. Like I mentioned before, for experimentation, I'm switching out the pre-training and fine-tuning steps and seeing which ones are necessary. And I'm also only using the front side of these pills just due to time. It's a bit complicated to try and use both. And it's a bit confusing how even the metric is evaluated when you get front and back sides of pill images. So as far as progress goes, the self-supervised pre-training is basically done. My nice pretty tools for displaying how things are going are done. The supervised pre-training is unfinished, and then my final training and implementation of the actual metrics for the benchmark are not done. To conclude this, I did print out, this is also from the model that is currently training. I ran it a similarity against the ePIL-ID data set. So on the left here, these are consumer pills. And then on the right, these are reference pills. And this is what it thinks is close. It does okay. I intentionally cropped this image because here it's actually getting these correct because these are each G5 or GS. It's hard to tell because of the reduced size. And they may even be wrong, but I'm still pretty happy with how close they're matching these symbols here. This one here has matched a little farther away, but it's still pretty close. Then here's a consumer versus consumer. So these are the consumer pills that it's grouping together. Again, same format. On the left here is like the key. These are the consumer pills, and obviously it matches closest to itself. And then these are the images it's deciding are close otherwise. And then similarly for the reference. And what I like to see here is I like the attention it's actually paying to these symbols over just the colors, because it actually shows that the network thinks that these are important. All right, those are my references, and that will conclude my presentation.
Okay, yeah, thank you, Ryan, for the presentation of the project. Yeah, I think this is very interesting. You did some self-supervised learning, especially you do some, injecting some of the random texture.
Mm-hmm.
So for your project, so this self-supervised learning you already implemented, right? So have you done with the training?
It is currently training. It's
okay.
like, I don't know how long I'm going to let it train for, but it's doing pretty well already.
Okay. So in addition to adding these different textures, did you do any other type of augmentation?
They are warped. They're okay. I think I forgot to mention. So they're warped and they're also color jittered. So like this pill right here is pink, but it's been color jittered up to this orangish color. Yeah. And the network is still actually recognizing that they're pretty similar.
I see. So one thing I was just wondering, like, for this is doing pill type classification, right? So is color like one important attribute? The network has to learn to distinguish different types.
Mhm.
Because you're doing this kind of jittering, right? But if color is one distinctive, attribute that is used to recognize different pill type, or maybe some of the pill type also may depending on the color, then this may confuse the network. Do you think?
It definitely does, and I observe that when I'm actually looking at the comparison that I currently have visualized in like a later slide. The thing that's tricky is one of the big problems that all the papers say about pill classification is color is incredibly important, but the network's ability to actually recover the color under different lighting conditions is really hard.
Mhm.
So I just decided I would like, if it emphasizes color, like I'll go back to here. Like I would like if it would emphasize color, but maybe it can pick out some other really important details. Like hopefully the labels, I think, are
Yeah.
probably the most important thing.
Yeah.
And my network is illiterate, unlike
Yeah.
Jacob's from last Thursday.
Yeah, right.
But
Yeah.
hopefully it can like at least figure that out.
Hmm. Yeah. And so can you also please explain a little bit like the motivation that you adding these kind of random texture? Why do you think about doing this kind of augmentation?
Um, there, I just kind of wanted to see what would happen.
Okay.
But the rationale I give now anyways is just I hope that it would do better than just like using a black background.
Hmm.
I hope injecting some other like patterns into the image which are not the pill would help it. The idea originally came from I was trying to segment the pills myself to get like a large pre-training data set. And so I slapped on these textures so that I could like generate synthetic images and know
Yeah.
where the pill was. But I just kind of carried that into my final project when I decided just to, reuse some already segmented ones.
Yeah, so I think rational definitely is very important, right? So because if you eventually writing a report or writing a paper, you have to explain to the readers, right? Or why are you coming up with this kind of idea, right? Why this is reasonable. So one thing you can think about is that, okay, so let's say the same pill, right? And I just augment different tech, background. So then still, if you consider that's a positive pair, if you're doing cell contrastable learning, and you have another different type of pill, that's a negative pair, right? So in a way, you enforce the network trying to pay attention to the pill itself, right? Because the positive pair, you have different texture background, then you still consider that as positive. It's kind of in a way to enforce the network to not pay attention to the texture or the background, right? Because even though they are different, but we are still considered the same type. So let's just focus on the pill itself in a way. So yeah, you can think about in this way and see if, and eventually maybe you can even visualize, right, how the attention has been, focused for the network.
Yeah, that would be really cool.
Yeah, to validate or justify, this kind of hypothesis or just conjecture, right? So I think this is, something very important, if you want to later write a paper or report. Yeah. Okay. Yeah, but I do, yeah, I think I also, want to mention, last lecture, Jacob's approach that is using the OCR. And you also mentioned, right, some of the text on the pill seems to have some salient information, right? Is able to help, identify a specific pill type. So yeah, I think maybe, like I mentioned to you guys before, right? So if you feel like there's something eventually can resulting in a very good paper, I mean, you can, Jacob, maybe eventually you guys can talk, maybe collaborate in the future, or after this course is done, right? Maybe your self-supervised learning plus, his, text or OCR detection, right? Together can, even strengthen or improve the performance. So that's some of the things you guys can maybe discuss, maybe explore in the future. Okay.
I do remember his project was like
Yeah.
he split the architecture. He had the part
Yeah.
OCR and then the part
Yeah.
that was like a regular feature
Yeah.
detector. So
Yeah.
yeah, if I took over the feature detector part, that would definitely be interesting.
Yeah, yeah. I think you guys are doing something different, right? Because I focused on, pre-training to learn a very good feature representation based on the appearance itself. But
Mhm.
Jacob's approach is kind of using another like we can say off the shelf, right? OCR feature detector, right? To extract those another type of feature, right? Those characters to help the pill recognition. So definitely, if the self-supervised learning does make a difference, right? Improve the feature representation, then it can be combined with the OCR feature together to further to achieve some of the improvement. And both of these ideas, the rationale is clear, right? So for your representation, you want to the network to focus on the pill itself, right? Learn some meaningful information. And for Jacob's approach is, this OCR seems to be very valuable information. And if we are able to clearly extract those information, it's going to be, very helpful to identify some of the pill cases. Yeah. Okay.
Yeah.
Okay, great. So let's see what the other student will have some questions or maybe suggestions for the project you have here. Any other questions, comments, suggestions? Okay, if not, so one thing, right, because the self-supervised training may take quite a long time, do you think you are able to?
Its way in. It's pretty funny.
Hello?
Hello.
Sorry, I think, yeah, my network that got disconnected. So where was I? Where did I broke up?
So there was one student that asked a question. They said that a good rationale for my background thing is the backgrounds for consumer images are unpredictable in practice.
Yeah.
So it would be likely that I would be hitting at least some of the textures, or maybe just learning a good feature representation from this.
Yeah. Yeah. Okay. Yeah, that's a good point. Another thing I noticed is some of the consumer images, they have like overexposure, right? Those illuminations got quite high, making some of the, those characters are not easily visible, right? Like slide 7. Yeah, those yellow ones, maybe. I was wondering, you can do some simple pre-processing like, histogram equalization or trying to enhance the contrast. You can using some of the easy, image pre-processing, like I mentioned, right, histogram equalization to enhance some of the contrast. Maybe that will also maybe something easy to do. May also give you some of the performance improvement.
Yeah, possibly. Yeah.
Yeah.
And even something like, I know other papers have they've done color images and also added like a grayscale layer, because in theory the pills should be the same regardless of, well, not for all pills, but for a lot of pills they should be the same regardless of color. The label should be the same regardless of colors anyways.
Yeah. Okay. Yeah. Okay. All right. Thank you for the presentation again. So let's move on to the next one.
I believe I was next.
Okay.
All right. All right, do you guys see my PowerPoint slides?
Yeah.
All right. All right, so hi, I'm Joe Fioresci, and this is my final project report. The topic is the malaria life cycle classification in thin blood smear images, which we've seen presentation on the other day. So just a general motivation is that, like a lot of things in medical imaging, early detection and identification is crucial for patient care. In this case specifically, we're dealing with different life cycles of malaria. So if we know the life cycle, we can identify the malaria, then we can give the patient the best care possible. And just the general issue is that identifying these is very time consuming. It's a mistake prone process. If someone's staring at images for 20 minutes or for a couple hours, or they're poorly trained, they can make some mistakes, and that could be very bad for the patient. So we want to minimize that. This image is an example of what they would be looking at, and it could take 10 to 15 minutes just to look at this image, which is only a small portion of a blood slide. So to view a whole blood slide, you got to do this over and over. And then there's just a large volume of images. Nobody wants to sit down and do this, so we need a way to make this faster. So the benchmark that was published was a data set called IML Malaria, and it consists of over 38,000 cells that are parsed from 345 different blood slide images. It has a very imbalanced distribution with less than 500 actual malaria cells, and the rest being healthy red blood cells. So the challenge is sort of overcoming this imbalance and still getting good classification results. So the approach in the paper, they start with the pre-processing, where they just take this image and segment out the individual cells. For the purposes of my work, I'm assuming that this is pretty successful and it segments the cells accurately. So I'm just taking these individual red blood cells and running a classification model. The state of the art that they published was starting with a binary classification network, where they simply said this cell is clean or this cell has malaria. And for this, they got best results with ResNet 50 v2. And then they took all the cells that were classified as malaria and ran them through another multi-class classification network. So this time it has a lot less class imbalance, but still some exists. And then they also use ResNet 50 v2, and they have this kind of two-step algorithm that gets their best results. So for my approach, I use a single stage classification with just ResNet 50. I don't use any fancy network architectures, just try to tune the hyperparameters and whatnot to get better results. It seems like for this paper, they were focused on getting a model that works well and runs on a mobile device. So it wasn't as focused on tuning the hyperparameters and using fancy data augmentation to achieve the tip-top results. So I'm going to try to do that for them, basically. So my current progress, I use just general data augmentation, some random transforms, pretty standard, using PyTorch. I do resizing, flips, 90-degree rotations, Gaussian blurring, normalization. I tried out a couple different loss functions, notably cross entropy and focal loss, and tried out SGD and atom optimizers, and focal loss and atom optimizers were the better of these experiments. And since we didn't really talk about focal loss in class, I don't believe, just a quick overview is it's meant as an improvement to cross entropy loss. Basically, it's designed for imbalanced data sets, mostly or primarily binary classification, but I had to adjust it for multi-class. I defined an adjustment. But the intuition is that you have these lower probability classes. If it's, let's say, the probability of that class showing up is 10%, the loss is seen up here, so it gets a much higher loss. But let's say there's the healthy red blood cells with 99% probability of showing up, it'll get a very low loss for a misclassification. So basically you get penalized more for the lower probability classes, which is very useful for the imbalanced data sets. This gamma term here sort of just defines the curve. What I found is that people find a lot of success with 2, so that's what I use. And then this is using just probabilities of binary classification, but in order to use it for multi-class, it didn't work the same way. So it just had to use class weights for a cross-entropy function, and then it basically modified it into a focal function. So I tried different class weights for this, trying to do inverse of just the proportions of the different classes, but I found the best results were just using the Scikit class weights. They just have a function for making class weights, and it seems to work best for things like this. So their results, they published both single stage classification along with the multi-stage classification, like with the binary first and then the multi-class, like I showed in the first approach slide. But so in their single stage, it seems like they compared to a previous work and a couple off-the-shelf algorithms. They got their best average F1 score of 75.52%. And then for multi-stage, they started with that binary. They got an F1 score of 89.91%, which is pretty good with an accuracy of 95%. And then they fed that into the multi-class network, and that got an average F1 score of 82.04%, which was just about 6.5% better than their single stage work. So my current results, this is a sklearn like classification report that gives the precision recall and F1 scores of all the different classes. So, and the support shows the like how many class examples there were, and this is in line with the full data set. So I just used the full data set here. And what I think is important to note is that recall is high for almost all of these, which in a medical field, recall is generally more important, because if we get, it basically tells you how many of that class that you find, or like the percentage of that class. So in a situation where the model predicts that a healthy cell is malaria, it's not as detrimental as predicting one of these classes is actually a red blood cell, because then it would go unnoticed, and that could be very bad for the patient. So I think even with this F1 score being dropped by the ring precision here, because it seems to be over guessing the rings, it still got very good recall. And so I was very happy to see that. And the average F1 score was actually 82%, which I thought was pretty cool. Again, like they didn't focus as much on getting the highest results possible, but I was still able to almost match their results with a single stage pipeline instead of the 2-stage. And so this is from their paper. This was their confusion matrix, and it seems pretty standard. They had a couple misclassifications with these more imbalanced classes. But so this, I had messed up, and I didn't have the confusion matrices printing when I found my best model. And since I wasn't focused on keeping each individual model to test on later, I was just training models over and over until I got the best results. I overwrote my model for this model. And so I had to quickly try to train a model recently. And I did less epochs. It didn't get as good a results, but it was just an example of a confusion matrix. But I think mine would look more like this if I had maintained the model from these results. But so this was just a direct comparison. You can see they had it flipped for some reason. I don't know why the healthy blood cells were in this second column instead of the top column. But like we see here, in this quick training, it wasn't fully trained, but we get these ring predictions were pretty highly correlated with the healthy predictions, which you can kind of see the same thing here. So I just thought that was interesting. There's some consistencies across both of these works. And so future work, I'm going to try more transform augmentations that we talked about in class, such as color shifting and random erase. Some common methods for dealing with class imbalance are undersampling and oversampling, where we'll take, for undersampling, we'll just simply take less of the healthy cells. We'll just eliminate a lot of them from the data set. And then oversampling, where we will augment and just use the imbalanced cells more than we use the healthy cells. So we like kind of take the same image, do some augmentations, and use it twice, 2 or 3 times to build another data set. And then there's also one thing I've seen with segmentation specifically is they found success with copy paste data augmentation. I'm curious to see if that works with classification, but the general idea is that you take a cell with, let's say in this case, you take a malaria cell and you just copy like the middle of the cell and you just paste it onto a healthy blood cell. So it sort of creates it's just another way of doing augmentations. It's a bit weird and it doesn't seem like that it would work, but according to this paper and a couple others, it seems to actually improve results somehow. So I do want to try this out. And yeah, that's what I had for this presentation.
Okay, yeah, thanks for the presentation, Joe. Yeah, I think maybe I can clarify a few things you mentioned. Yeah, this focal loss, yeah, definitely is very useful. So it was originally proposed for object detection, right? So for object detection, the object of interest may only like may one or two like person, right? If you have a person or dog, a cat in an image, right? So the positive, bounding box may only a couple of them, for the candidate, but you do get a lot of background bounding box, right? So then that's going to be a highly imbalanced, right? So how do you suppress some of how do you classify this is a foreground or this is background, right? Based on these different imbalanced distribution of these different bounding boxes. So that's why they using these focal loss to penalize, these penalize more on the low probability, classes. And we talk about something similar, which is when we talk about the brain tumor segmentation, right? We use the Dice loss, right? So I talk about the weighted Dice loss, right? So for the brain tumor, it's also kind of imbalanced, right? For some of the tumor classes, it has more, ground truth pixels. For some of the tumors, like enhanced tumor, you may only have a small portion of those pixels. So for the weighted Dice loss is that, based on the ratio of the pixels in the training data set, you want to do the inverse, right? When you compute the loss, you want to do the inverse ratio, right? It's kind of like here, right? You have these kind of, less probability class or minority class, you will have large penalize more, right? Because you don't have a lot of training sample. You cannot afford to make too many mistakes on these minority class, right? If the model does make a lot of mistake on these classes, then the model doesn't do a good job, right? For these kind of classes. So we don't want that. We want the model able to learn good representation that is able to recognize different classes maybe equally. Okay, so yeah, so that's the similar idea for the focal loss, or if for the medical segmentation, there has weighted Dice loss. Okay, and so I think this is good. You found this focal loss and kind of address these kind of imbalanced problem. So in your experiment, have you done any ablation study? Like if I just don't using the focal loss, I just using the ordinary binary coarse entropy. Did you see what's the difference in terms of performance? Have you conducted this kind of analysis?
Yeah, so I did it, and I just saw better results overall, and I just went with the focal loss. At the time, I didn't have a confusion matrix implemented, so I think I can go back and definitely do that and see what kind of things I notice with the specific differences.
Yeah, definitely. Like in your final report, these are some of the important things, right, or important pieces or component for your approach, right? So you want to justify or validate the effectiveness of these different components, right? How much improvement this focal loss, bring to the final accuracy, right? So if you can show that this focal loss does make a difference, then this is a good way, you put it into the right use, right? If it doesn't, then what's the point of using this focal loss? So I think that so that's one important things aspect we can do, or you can show in the final report. Okay. And so yeah, I guess one advantage for your approach is this is a single stage instead of just two stage process, right? So it's going to be simpler. You just have a one network and you can directly get the result. And I think on the last one you mentioned do some copy paste. You haven't tried that, right? That data augmentation.
No, I have not. I'm currently working on like I have code that tries to copy paste, but it's being weird right now. So I'm trying to finish that and then start using it to train.
Okay. Yeah, this is very common. Like do people in like do object detection, they also do this kind of copy paste, right? You have this foreground, then you can paste on any of the background. You generate another data because you have the ground truth bounding box. Here, similar. And even for segmentation, you can also do copy paste, right? So for the training data, we have the ground truth, right? For the brain tumor segmentation, for example, you can also do this kind of copy paste. Take some of the tumor pixels, right? Paste that, on some of the healthy tissue regions. So that may also increase. Another way to kind of address the data imbalance issue, right? So for some of the classes don't have many pixels, then you can take them and copy some of the pixels to some of the, healthy tissue region. But I don't know if this will may not have a very strong physical meaning, right? Because these medical images, corresponding to some of the specific pathology, right? Those tumor, how it grows, evolve during the time, but this kind of random process may destroy those kind of patterns. Yeah, but I guess for your case, you can also try that. It's simple to do, right? Copy paste and see if that also give you some boost of the performance. Okay. Okay. Yeah. Any questions, comments from the student? Okay, great. If not, we're gonna move on to the next presentation.
All right, thank you.
Thank you.
Okay. I don't know if I'm next in the list, but I can go.
Yeah, I think you are right. Yes, I think you're the last one for today. Yeah.
Okay. All right. So the problem that I was trying to address, models are trained that are trained on one data set. They rarely generalize well on unseen data. This is just as true in federated learning. And so I want to try to perform well on a new data site without sacrificing performance on other sites. The paper that I presented before in class, as they trained, they had this concept of like a target site, and they trained for that specific site. And ideally, you don't want to sacrifice performance on some sites. So the basic idea that I had is while federated learning does not allow sharing actual data samples, we can share feature vectors. And basically, I'm treating each site as its own domain using a shared encoder model and a site-specific final embedding model. And I'm trying to identify samples in an unseen data site with known labels from known data. So each site uses the same feature embedding function that takes your samples and embeds it into a feature space. And for each site, they're going to train their own latent embedding function that takes those feature embeddings into a latent space for that specific site. And the loss that they use is basically a clustering loss. So this is cosine similarity. You want the cosine similarity between two samples to be high if they have the same label and low if they have different labels. And so this is going to generate a cluster for each class in the site S, and for each class, and this is in that site's latent space. Finally, once we have these special G latent embedding functions, you evaluate on a new site, and you want to try and match the unknown labels with known labels. So the experimental setup that I have is I use the CFAR 100 dataset, and this is just to test the feasibility of my idea. You know, uh, ideally, or for the actual final experiment, I would use an actual medical image dataset, but this is just to test how feasible this is. So for the CFAR 100, they have 20 course labels, and those course labels are what I'm using as the label. And then I'll arbitrarily put each one of the fine labels into one of 5 sites. And I'll train, and I trained on the first 4 sites. And this gives me, for each site and each class, I can get an average latent vector for each of those. And then finally, I evaluate on the final site, and I obtain just a feature embedding. So I haven't sent this through a G sub whatever. This is just sending it our original sample through X, and we're getting a feature vector for each class. And then I compute a cost where I say the similarity between this feature vector for our unknown class versus one of our known classes is given by this function. So this, breaking this function down, you have a latent feature vector for a certain site in a certain class, and an embedding function for the same site of this feature vector that we obtained. And we want to take the maximum similarity over each of the sites. I tried a few different methods of doing this. This is just what gave me the best results in the end. But I tried using like a mean, and I'll get more into the how this can be improved later on. But this is just the experiment that I did. And so once we have this cost, which is minus the similarity. So we're saying how similar this unknown class is with each known class. Once we have the similarity, we can take minus that to get the cost. And if you have a cost matrix, you can perform a matching using some standard algorithm, Hungarian algorithm, whatever one you want to use. And so for the results, originally when I submitted my report, that was, what was it, last Friday? In my report, what I stated, I actually had worse results than I have now. I submitted that, and then really early on the next week, I was able to improve my results. At the time, I was getting no better than random chance, but I eventually found a bug. So the metric that I was using for similarity at inference was different than training. So for random chance, you would get a matching with 1 correct on average. And I was able to get consistently 3 correct out of 20 matching accuracy. So analyzing this, I think I should have leveraged more vectors here. I was really just using these vectors at inference time, but I should have used them during training more extensively. And CFAR 100 is probably not a good toy data set for this. For next steps, really, for one, F should have been learned from the data in a federated, self-supervised manner. I used some fixed F for a proof of concept, and I do wonder if there's a way that I could maybe learn these GS using information from other sites. And I have some planned follow-up experiments, but those won't exactly work on CFAR 100 because the CFAR 100 sites are really random. There's not good. You shouldn't expect that any 2 sites are going to be more similar, and that's something I would want to leverage. So yeah, I would want to be able to say, I would want to be able to detect automatically if two sites have similar embeddings. I would want to be able to say that they're similar somehow. So when I test on a new site, I should be able to evaluate some samples and say, hey, the distribution of this data looks really similar to site 3, and use that embedding function more. But overall, I'm not so sure if this was a good direction, and I'd love ideas and suggestions. But
Yeah.
really, I think I need to read more papers and adjust significantly. Um, I do have, if you guys want more an explanation on how this matching is done, I can give that as well.
Yes. So yeah, thanks, Zach. So is that it? Before I give you some.
Y- um, yeah, I do have some information about how the matching was done, but
Yeah.
maybe that's not
So
so important.
yeah, I guess you want to explain the problem more clearly. So understanding you want to do some, seems like this, you want to do some domain generalization, right? So you have different sites, right? Maybe the data distribution are different, right? The feature
Yeah,
representation may be different. You may
yes,
not able to generalize well to some of the unseen sites. So you want to do some domain generalization. Here, can you go back to the setup you have using the CFAR 100?
yeah.
Oh,
So,
yeah, when you say there's how many classes are there?
so for CFAR 100, there's 20 course labels and 5 fine labels for each course
So
label. So that
yeah,
gives you a total of 100.
yeah,
But I'm treating the course labels as the labels that I'm trying to assign to.
yeah. Can you
So I only really
explain?
regard those.
Yeah, please explain what does course label and fine label mean? Like, can you give an example?
Yeah. So for instance, there's the course label that's person, and so there's man, woman, boy, girl, baby. Those are all humans.
I see.
Um, but there's different examples of those. So, maybe one site is a works with children versus another site that works with mostly adults. Um,
Yeah,
that could be an
so
example.
I see. So they all structured in this way. Maybe there's another class like flower, then there's, different types of flower names, or maybe there's a, class of dog, then there's different breed of the dog. Is that what you mean?
Yeah.
Okay.
Yeah.
Okay, so yeah, we understand that, right? So it's kind of, there's a fine grained label under each of the course label. So here, you arbitrarily put each fine label in one of 5 sites. What do you mean by this? Like, how do you distribute the label?
So, so each course label has 5 fine label examples, and I put the first fine label of each course label into one site, and I put the second fine label of each course label into a second site. And that gives me 5 different groupings of one example of each label.
Okay, so let's still like make things simpler. Okay, let's just say you only have one fine label, okay, in the entire data set. That's like people,
One
okay?
course label?
Yeah, let's just make
Okay.
it easier, okay? Understand how
Okay.
to do the setting. You
Yeah.
have one label that's person, right?
Mm-hmm.
And under this course label, there's like a man, woman, boy, girl, another one. So there's a five fine labels. So can you explain how do you do, like you have men in one side, woman in another side, and boy one side? Is this how you distribute the labels?
Yes.
Okay, so then if I have another course label that is car, right? Then maybe under that car I have, sedan, SUV, minivan, truck, then you do the same, right? One
Yep.
side, randomly choosing one side, put put truck, and there's another side has minivan, etc. Right? So you distribute in this way.
Yeah.
So, but overall, each site will have these 20 course label, right? Or has samples coming from these 20 course labels, right?
Yes.
And because you distribute the final label differently, right? So maybe this site will only have cars, boys, but the other site will have like a truck, woman, right? But
Yeah.
in a way, you make it like there's some domain gap, right? Although they have the same 20 course labels, but the final label are different. That's why there's domain, right? Because like minivan, truck may be different, although they have the course label as car, but they do have some difference in terms of appearance, right? Feature distribution, feature presentation.
Yeah.
So that's the idea. Okay. Okay, so that's how you distribute the labels and the samples. And how do you do the training and the testing? You train on 4 sites and then you test on the rest?
So there's only 5 sites, so I train on the first 4, and then
Yeah.
I test on the 5th site.
Mhm.
And it's and the idea is that I take some examples from each class, and then I try to match them with the original 4 sites. So this C prime is a test label, and we're trying to find a correspondence between those test labels and the ones that we had at training.
Yeah, so here, are you only consider like a 20 course label in this case, right? You don't consider like.
Yeah.
Yeah, so in your classification problem, you only have 20 course labels, right? So that's why you can, you still like if the test set has a minivan, but all the other 4 sites don't have minivan, but have truck, sedan, but they are corresponding to the course label of car. You still want the test that this minivan is able to label as a car. Is that right?
Yes.
Okay. So here you basically just find the feature and do some you obtaining the feature, basically just like doing some feature matching and find the closest one.
Yeah.
Okay. Then what is the strategy you address this domain gap then? I mean, this is just like a standard, you do the training, you get the feature, you do the match. Then what is the technique you use to address these domain gap then?
So this was I mean, this is just the milestone. This is was supposed to be my initial test to sort of show the feasibility. I wanted to try and do something with, I wanted to use this as a test, get some results, and if it looked good, then I was going to try and get more genuine data sets and try and find a way to use the similarity between sites and to sort of, so for a certain embedding, let's say site 5 is really similar to site 3. I should be able to, when testing, identify that the third embedding function is actually really useful. And I should be able to then use that knowledge to better classify on the 5th one. I wasn't particularly happy with the test results that I have so far, which is, yeah, so my results are not satisfactory for my own standards. So
Yeah,
that's
I
where I'm at.
understand. Yeah, so there's a process, right? Maybe we don't get the perfect result we want in the first place, but we need to know, right? We are doing the right procedure, right? We understand the problem setting and we know what to do, right? If we figure we doesn't achieve the expected result, right? What's the problem? We can have a solution. So, you know, I think for you right now is you have this kind of initial result, right? Just playing, you know, doing some feature extraction and matching and get the classification result. What I'm understanding is that you never go into the technique, you know, how to address this kind of domain gap issue, right? Which seems to be you are trying to solve in this case. What I suggest you to do is, since you review that paper or you present that paper in class, right? So what is the technique they use? Maybe you can take that, right? Implement yourself and see if it works or not, right? So you have the baseline and maybe implement what they propose and see if it's gonna work, you know, improve the result. So do you know how they, what is their approach to solve this kind of generalization problem?
So the way that they do it is they actually have access to the test set beforehand. And they evaluate certain samples, and then they don't have the label, but they use that feature embedding to sort of prime the other sites in their training to be able to deal with those types of samples. The exact way they do that is they share a feature embedding, and then each individual site trains a discriminator to tell whether or not it came from the target site. And then the encoder at that site tries to fool the discriminator. And that teaches the encoder to use a feature space which is more, I guess, more amenable to use at the target site.
Yeah, so I think, you know, when you get into feature learning, things can be very complicated, right? So the different settings, what kind of information you can gain access to, right? So I think for your project, you can keep it simple. Maybe you don't have to follow their setting. In this case, then maybe there's a lot of things you have to do, right? You train like a GAN, right? There's additional things you have to train, and you know, you may run into other problems. What I would suggest you to do is, since here, another aspect you can look into is from the metric learning standpoint, right? So you have these feature matching, right? So here, how do you, what is the metric that you are using, like a Euclidean distance or whatever the distance you have? How do you do the
Cosine
metric?
similarity.
Yeah, cosine similarity. So I can suggest you a couple of things to look into. So in the metric learning space, there's you know, all kinds of, you know, metrics you can using, right? Euclidean distance, you know, cosine similarity, and maybe other metrics, you know, for like personal ID, face verification, right? You know, all boils down to metric learning, right? Because you want to do the match on like a, you know, a fingerprint, you know, recognition or identification, right? So all comes down to metric learning. So maybe you can look into that and see if you can have a better metric, or maybe try a combination of different metrics, right? You don't have to using one, right? Maybe have a couple of them and have some different weightings, and see if this will give you some of the, you know, robustness, right? If give you better result in terms of this kind of feature matching, if there's some of the domain gap. So that may be a easier way to look into and see if you can come up some strategies to improve your current baseline result. So that's one of the recommendation. Another thing is, I was wondering if you can do some, yeah, contrastive learning things. right now. Yeah, in a way, you can do some in your test set, right? You can do some contrastive pre-training. Maybe that will also improve the generalization of the feature presentation, right? If let's say like a truck, although couldn't change augment to like a minivan type of thing, but you get the idea, right? So you have different augmentation, it will somehow improve the generalization, have a better representation. That could also, improve the performance as compared to the baseline you have right now. So that's another thing you can look into.
Okay. So augmentations on the test set, you mentioned some loss functions that are used in ReID and
Yeah, the
other
metric
settings.
learning, the metric learning just have some, come up with different, metrics for the feature matching. So that's one aspect you can look into. If you want, I can share some of the papers, literatures. You can look into that and see if that can make some of the improvement. Yeah,
Okay.
but overall, I think when first listen to the presentation, I don't get the overall problem or idea clear. So I think this is something you have to improve for the next couple of weeks. When you do the final report, you have to make the problem, the experiment setting very clear, right? And, justify the rationale, and also, demonstrate if you are addressing this kind of generalization problem, right? You have to present what's your solution then, right? So if you don't do anything, it's just basically get the feature, apply it to this test site, then do the matching. I don't see any, specific solution that you're trying to address, how you solve this kind of generalization issue, right? So if you want to do that, you have to show, right, what is your solution for that. Otherwise, maybe you have to restate your problem. Maybe you're solving a different problem, right? So that's the suggestion for you. Also, in terms of the methodology wise, right? Metric learning, maybe so you can look into that. You can find some other metrics or combination, a couple of metrics together to see if you are able to somehow mitigate this kind of generalization problem. So, because time is limited, right? You don't want to go to something very deep, then, you end up with, a lot of stuff to dealing with and very complicated. That's not good, right? So for now, you can have a very clear direction, very simple one. If I try this, may work well, right? These different metrics, very simple to do. You can try that and see if we are able to improve the result. Okay, so that's my suggestion. Then you can, focus on how can you write the report clear, right? The problem, the solution you have, and show the result to justify that. So I think that will be good. Instead of trying different things, but nothing works, then that is not how we learn from this, doing this final project. Okay.
Okay.
Okay. Yeah. If you need more guidance or suggestions, feel free to let me know. We can, set up, individual meetings to discuss some of the details. Okay. But I think, you still have some time. Just focus on something very, not very broad scope, just a simple one, and see if that will, address or somehow, improve the performance and achieve, what you originally proposed to do. Okay. So that's my suggestion.
Okay. That sounds good. Yeah, I'll probably message you
Yeah.
About that.
Yeah. Okay. Yeah, but I think your problem is interesting, quite challenging. So, learning a very good feature representation is a very difficult task. And if getting into the feather learning can be very complicated, right? Because dealing with, how you are not able to, what kind of information you can share, right, with different sites. So that could be quite challenging. So my suggestion is, you don't have to go with too complicated. Just have a very clean, you have a simple setting that you are able to focus on one aspect and try different things to make your method work. So I think that's the important thing. Later, you can look into more challenging or more difficult cases, right? More complicated cases. But in the first place, we want to have a very simple baseline, right? Just solving just one single problem, right? From one aspect. If that works well, then, you can keep building upon that. Okay.
All right.
Okay, great. Is there any other questions from the student or suggestions, comments? Okay, so yeah, I want to maybe have final comments on the final report. I think some student asked me about how should I write the final report. So because we have like proposal milestone, right? So for the final report is you can pretty much based on the milestone report, because I think your milestone report will already have like problem statement, what's the proposed method, right? What kind of data set you want to evaluate. And so you can take that, and for the final report is just you have to adding some extra result, which you haven't finished before, and some of the analysis. You can refine some of the introduction section, related work section, based on the milestone report. But yeah, basically just finish or wrap up everything, present the final result, some of the analysis. Okay, so that's your final report. But a good final report I want to see is you have a very clear presentation of the problem, what you are trying to do and what is the method you propose, right? And then the rationale is very important. Why do you propose this kind of technique to solve this problem, right? What's the rationale for it or motivation for that, right? And also in the experiment, you want to justify that, right? So like I mentioned one example, right? If you're using the focal loss, right, as your maybe one big component in your method, right, to address this imbalanced distribution or data, and you want to verify that in your experiment, right? Does this make a difference? Does that solve the problem, issue you mentioned earlier, right? So I think those are some of the very good analysis you can put in the final report. Okay. All right. Are there any other questions? Okay, if not, we're gonna end here. We're gonna continue the presentation on Thursday. Yeah, on Thursday there's 5, so I have to precisely cut down. When you overtime, I will let you know. Okay. So be prepared for the presentation, maybe just around like 7 or 8 minutes. Then, so I can spend some time to give you suggestions or maybe ask you questions. Okay. And in the meantime, so when you kind of finish off your project, if you have any questions, if anything you don't clear, let me know. I'll be happy to set up individual meetings with you guys, to polish your result. And eventually, if you think your result is good, right? Based on the literature survey you did for this topic, if you think your result is state of the art and your method has some novelty, talk to me. I think maybe we can, try to publish your work into some conference, maybe extend it to a journal paper. Okay, so that's you have that option there. Okay. All right, thank you guys. We're gonna end here and I'll talk to you on Thursday. Okay, all right, have a nice day. Bye.